All right, thank you for joining us on today's webinar, Enabling the Metaverse with 5G. My name is Ben Stone, and I'm with RCR Wireless News. 5G is going mainstream across the globe, and this is an exciting time to harness the low latency and high capacity of 5G to enable the metaverse. Your speaker today will be Hemant Sampath, Senior Director of Engineering, Qualcomm Technologies. As a note, the webinar and the slides will be available for download after the presentation today. Please be sure to enter any questions that you have for Hemant during the presentation as well, and we'll do our best to answer them or follow up with you after the webinar via email. With that, I'm pleased to give you Hemant.
Hello, everyone. Thanks, Ben and RCR for this nice introduction, and welcome everyone to this webinar on enabling the metaverse with 5G. So 5G is delivering on the vision where virtually everyone and everything is intelligently connected, whether it's industrial 5G networks or automotive, or even enabling the metaverse or 5G positioning. The thing about 5G is that it is built from the ground up for low latency and high reliability applications like XR. And these can include features such as shorter time slots, especially for the mid-band and millimeter wave, as shown in the figure, or faster processing times in the form of front-loaded downlink control channel, or faster AC and CQI response times, or faster uplink transmission times in response to a grant. It also has reliable beamforming features, both in sub-6 and millimeter wave, which improves reliability and also enables low latency and high reliability transmissions, which is great for applications such as XR. So when we look at XR, they're broadly categorized into two categories. On the left, you have VR, or virtual reality, wherein the user is fully immersed in a virtual environment. Or you can also have AR, or augmented reality, wherein augmented information is sort of displayed or superimposed onto a physical reality. And the applications can range from consumer applications such as fitness, gaming, and entertainment, or shopping, or enterprise applications such as corporate training, education, and remote assistance. And we've all heard of this term, the metaverse. When we refer to the metaverse, we essentially mean a persistent spatial internet with personalized digital experiences. And this spans both the physical and virtual worlds, as you can see in this picture. And today where we are is it started with VR, and now it's morphing into augmented reality and mixed reality. And Qualcomm from Snapdragon, we have a lot of platforms to make it your ticket to the metaverse. So in terms of XR device roadmap, we see this as longer term evolving to be the next computing platform. What we see in the market today are, on the top left, you see standalone VR and AR devices. These are mainly powered by Wi-Fi kind of connectivity. And where we see that moving in the next 1 to 4 or 5 years is to have 5G connectivity. And the reason why we would need 5G connectivity is especially for private network, industrial, and enterprise applications, or even arena gaming applications, where you can have a lot of these devices in a small area, and you need to ensure low latency and high reliability and high bandwidth communication. And so 5G is a very natural candidate for it. But if you're in a home with 1 or 2 users, then Wi-Fi is perfectly fine, which is what we have today. On the bottom left, you see AR devices, AR viewers. And the way it's enabled today is by tethering. You can, for example, buy a Motorola handset, which is connected to a Lenovo-based AR glass, which has Snapdragon platform, and they are tethered via wire. Where we see that moving in the next 1 to 4 years is that cable is going to go away, and it'll be a Wi-Fi enabled AR viewer, which is tethered, wirelessly tethered to a 5G enabled smartphone, which is then talking to the cloud. We believe in the after the next 1 to 4 years or so, these two tracks are going to merge, and you're going to have the next platform, which will have both 5G and Wi-Fi, and will not only talk to any adjacent companion device, but will also talk directly to the cloud. And this, in the long run, then sets the stage for the 6G metaverse, where an underlying theme is the fusion of the digital, virtual, and the physical worlds. So what enables a rich XR user experience is this concept called distributed compute architecture. And I'll describe that in this slide. As you can see, in a distributed compute architecture, you have algorithms and processing that happens on the XR device, on a companion device such as a phone, and also on the cloud. Now let's look into what algorithms are run where. On the device, you typically want to run very low latency and low power processing, which are directly processing information from the sensors. And these are referred to as perception algorithms, as indicated in the figure. And the perception algorithms then produce information such as 6 degrees of freedom, head mount display pose, or controller information, or eye and hand tracking information. These are then shipped upstream via 5G connection to the cloud, wherein you have high performance graphics rendering and encoding that happens by using high powered GPUs and CPUs. These compressed rendered frames are then sent downstream via a high bandwidth 5G link. And then on device, you further have some post-processing. You'll have decoder as well as post-processing such as ATW, or asynchronous time warping and space warping of these frames, as well as techniques like error concealment so that the user does not see as many errors in the frame, and they essentially get a very good user experience. So this end-to-end round trip latency, right, which is from the device all the way to the companion device to the cloud and back onto the device before it gets displayed, is called motion to render to photon latency, or M2R2P, as shown in the figure. And this M2R2P has 3 components. You have the edge or the cloud processing. You also have the 5G and Wi-Fi round trip times, the wireless round trip times, and you have on-device processing. And we'll refer to both the 5G round trip times and M2R2P in the upcoming slides. So where we are with respect to boundless virtual reality is that it's really ready for deployment in private networks using 5G. And this could be, as I was mentioning before, industrial applications, like corporate training, education, as well as arena gaming applications, where you may have a larger density of users in a building or in a private network. What we have done is, by using our Snapdragon XR2 platform, which is a reference design which has our X55 5G modem, and by working with our infra partner Ericsson, we have demonstrated that over millimeter wave, that in a single 100 megahertz bandwidth with a single G node B, you could support 6 users in a single G node B. And then if you want to scale it, you could add more G node Bs, and you could pack up an indoor or an indoor-outdoor setting, a private network setting, with a large number of these devices. What Qualcomm has also done is put in a lot of on-device optimization beyond what's available in the standards. And we have secured about 25% or more tail latency improvements, and less than 20 milliseconds of 5G round trip time, as shown in the figure. Now, when you have 20 milliseconds of less than 5G round trip time, and when you add in the edge processing and the cloud processing, your overall M2R2P latencies are less than 70 milliseconds. One point I'd like to call out is this on-device optimizations, wherein we've reduced the tail latencies. And this is a very important figure, because at 90 frames per second, even if 1% of the frames are in error, that's really once a second. And that makes for not such a good user experience. So it's very important to keep your 99th percentile tail latencies as low as possible, and not just the average latencies. And we have successfully concluded like operator trials with AT&T and British Telecom, jointly with Ericsson, and we're now ready for deployment in private networks. Now, let's take a look at boundless augmented reality, wherein, as I was mentioning before, every user who has a phone can now get paired with an AR glass that's talking over Wi-Fi to a 5G capable phone that then talks to the cloud. And this way, you can really deploy this technology in a wide area in a network. And at Qualcomm, we did exactly just that, and we demonstrated our cloud to phone to AR glass, wireless, like readiness in this year's Mobile World Congress in Barcelona. And this, as I was mentioning, it really targets wide area deployments. And what we did is by using by using an infrastructure, and we actually put the user at the edge of the cell, at the far cell in a sub-6 gigahertz network, where the 5G can experience a lot of retransmissions and poor packet error rates and so on, as well as subjected the user to roll, pitch, and yaw, where the user is sort of looking around. And we try to optimize the 5G and Wi-Fi round-trip latencies. And I'll show you the demo shortly in the next slide. But really, we're able to get to, with our on-device optimizations, both on Wi-Fi and on 5G, on the device that is on the glass and on the phone, we're able to get 38% tail latency improvement. And we're able to squish in the 5G plus Wi-Fi round-trip times, even at worst-case scenarios, to less than 30 milliseconds. Here, I want to just mention that that for more immersive mixed reality experiences purely in an indoor environment, you really want the 5G plus Wi-Fi round-trip times to be less than 20 milliseconds. But here we're really talking about outdoor applications. So let's look at the video demonstration, which we demoed at MWC. As you can see, the user is placed at a far cell. The user is looking around, is subject to roll, pitch, and yaw motion. And on the bottom right, you see this 5G plus Wi-Fi round-trip time. And you see baseline performance, which is in the black curve. You see latency spikes from 60 to 70 milliseconds in just a 30-second time window. Whereas with our optimization, we have kept it to less than 30 milliseconds for the most part. And we're seeing about 38% tail latency improvement. And in the upcoming Mobile World Congress, we're going to improve upon this, and we're going to show you more. So stay tuned for that. So beyond the phone to glass architectures, where we see this going longer term, as I was indicating in our XR roadmap slide, is really 5G powered AR glasses, which can not only talk locally to the phone via Wi-Fi, but also directly to the cloud with 5G. So what are some technologies that are needed to make this work? First of all, we need optimized edge processing. We need to migrate from the central cloud to the local cloud. We also need better infra schedulers in the form of better delay-aware schedulers to meet the latency QoS. And we're working actively with our infra partners to achieve this. On top of it, we need to also pay attention to some of the evolving low power, low latency 5G features, which are being released in 3GPP. And I'll spend the next 20 minutes or so talking through these features. In addition, a very critical aspect to make this use case viable are 5G modem APIs. At Qualcomm, we've put in a lot of on-device optimizations, low latency optimizations that can be made available to the applications to get a better user XR experience. In addition, we do things like providing an API that allow applications to adapt to dynamically changing RF and network condition that leads to a very seamless user experience. I'll talk more about this in the next few slides. So let's take a look at 5G modem APIs. So these are APIs which are provided by our modem, and they talk directly to the application. And the applications, once they avail of it, it triggers a whole bunch of underlying modem features, which are carefully optimized for application requirements for the exact application in hand. And these include a variety of features such as packet prioritization. Is a packet high priority or a low priority? Is a flow high priority or a low priority? Better beam management, carefully taking into account the unique characteristics of a XR mounted headset, which are quite different from that of a handset, as well as dynamic packet processing on the 5G protocol stack. So we've taken a lot of care on our modems, going all the way from PHY, MAC, RLC, and PDCP and SDAP layers to make sure that the packets arrive in time. The high priority packets arrive in time for the application that's running on the device, and the packets and the frames can be decoded in n milliseconds. In addition, we also have 5G modem API, wherein applications can use this to dynamically adapt its video quality and rates, as well as experience less stuttering. We demonstrated this at Mobile World Congress earlier this year using a cloud gaming application. And I will now show you a demo video. Sorry, there's a plane flying right over my head, so I'll just pause for 20 seconds. Okay, great. So as you can see, on the left side, you have a baseline system which does not take into account our 5G modem APIs. And you will see the application stutter. And the stuttering is indicated with an hourglass signal, like a sign that you should be seeing if you just pay. You should see this hourglass pop up, which indicates stuttering. And then on the right side, you should see no hourglass signals pop up, which means the application is able to dynamically adapt to the changing RF and network conditions. And we have demonstrated this both in a millimeter wave setting, wherein it could be a lot more abrupt, as well as in a sub-6 network. In fact, the video that you're seeing was actually captured from a live network in Shanghai in a sub-6 network, where a Qualcomm employee essentially took the device and moved from near the window where there was very good 5G signal and moved towards the stairwell where the RF quality started deteriorating. And we continue to add more and more features to this 5G modem API, and stay tuned for the upcoming Mobile World Congress in 2023 in Barcelona, where we'll demonstrate more of these APIs. Okay, so now where is 3GPP headed? 3GPP is developing 5G advanced on the path to 6G. So we should really think of the 3GPP evolution in three buckets. Bucket number one was release 15, 16, and 17, which really provided a uniform platform for innovations. And we'll discuss some of the features that it introduced. The next bucket is 5G Advanced, which provided the second wave of 5G innovation, starting from release 18, where there's a work item for XR and how do we make for a lower latency and a higher scalable XR deployment over 5G. All this eventually leads to 6G at the end of the decade. So we're steadily progressing towards that. And now I will discuss in more detail some of the standards features. So if we take a one-slider shot of what did release 15, 16, and 17 do for XR, at a high level, we can say that release 15 and 16 introduced low power modes. And a very simple way to understand this is features such as bandwidth part. That is, if you have no or lower data, then essentially the modem goes into a smaller bandwidth. You also have features like cross-lot scheduling, which introduces gap between the control and the data transmissions so that the modem can go to sleep. So essentially trying to reduce the bandwidth and trying to enable the modem to go to sleep if there's little or no data, right? Release 16 introduced a lot of uplink enhancements, wherein you have traffic such as pose and tracking, and uplink configured grant really helps you to handle this periodic traffic much more effectively and with lower latencies and lower device power consumption. We also have features such as slot aggregation, which reduces HARQ latencies and uplink skipping, which saves power if no data. I will discuss in the next slide a little bit more detail on these uplink enhancements. But in the meanwhile, release 17 also introduced XR burst handling in the downlink, a feature called PDCC-H skipping. The PDCC-H stands for Physical Downlink Control Channel, and it really enables faster transition to sleep after an XR burst. So let's now look into a little bit more detail on the release 16 uplink enhancements. So as I was mentioning in the previous slide, release 16 provides for better handling of uplink XR traffic. It reduces latency and device power consumption, and let us see how we actually go about doing that. So as an example, AR uplink traffic, we've included pose. Maybe there's an uplink video information in terms of what the camera is seeing, as well as hand tracking. You could also have other flows such as head tracking and eye tracking and so on. But as a representation, let's consider these three flows, which can happen at different cadences and periodicities. Uplink configured grant essentially tries to align or basically provide for periodic resources for such low latency traffic. In this case, you see uplink configured grant, which is somewhat aligned to the pose information. And so this pose can be readily transmitted. Slot aggregation really involves improving the reliability and reducing HARQ latencies by allowing repetition in the next uplink slot. And so the idea is that you don't want to you want to make the pose information as reliable as possible, and you want to do slot aggregation. And then uplink skipping, as the name indicates, is really about if you have no uplink traffic, say in a particular instance, as shown here as a representation, if there is no pose information, then the device can just skip this uplink grant and not transmit anything and save power. So these are some of the uplink techniques which release 16 added, which is going to be pretty important prior to release 18 if you have to enable 5G based XR services, whether it's on a direct 5G connectivity or via the phone. Release 17 also introduced RedCap or NR Lite, which can also enable a category of low power AR glasses, which can talk directly to the cloud. As shown here in the figure, it has features such as narrower bandwidth, 20 megahertz bandwidth in a sub 7 gigahertz band, as well as the ability to have fewer receive antennas, 1 to 2 RX instead of 4 RX. These two features would essentially mean there's reduced power consumption as well as supporting lower data rates. And what we have found by doing our network simulations and doing a whole lot of analysis is if you have data rates of less than 10 megabits per second and you want to get a service going, like even at the cell edge and support many users, then RedCap is a very viable solution for such categories of services. Also, RedCap, there is only lower order modulation. There is 256 QAM is optional, as well as there's no features like carrier aggregation or dual connectivity, which essentially makes for a lower complexity device. As I was mentioning before, release 18 has a dedicated work item for XR. And from Qualcomm, we have a comprehensive package where we proposed features to lower the latency and lower the power and improve the capacity, system capacity, and to make XR a highly scalable and a viable experience. And I will discuss each of these in more detail, in the next few slides. But at a high level, it's really, we've introduced a lot of intelligence to take multimedia into account and not just IP packets. So QoS is defined based on multimedia payload. We're doing a lot of work to align the multimedia transmissions to 5G transmissions. And I'll talk about that more in the next few slides. Okay, so now let's look into some of our Qualcomm proposals for Release 18. Release 18 aligns the 5G transmission times to the multimedia cadence. And this is happening both in the downlink in the form of enhanced CDRX and in the uplink in the form of enhanced configured grant. I'll demonstrate this or sort of illustrate this by using an enhanced CDRX example in the downlink. See, what happens for multimedia is that they have burst arrivals, which are in the form of frames per second, and these run like 60 frames per second, 90 frames per second, 120 frames per second, and so on. In this example, we have used 120 hertz or 120 frames per second. And what it means is that these XR bursts are in the time domain, they are 8.33 milliseconds apart. If you look at the CDRX cycles, which were allowed in the 5G standards prior to release 18, you either have a choice of 8 milliseconds or 9 milliseconds. And it doesn't take long to realize that since they're not aligned to the burst, so there'll be a drift between the multimedia traffic and the 5G transmission times or 5G reception times. And that really means the modem has to stay awake longer. It may also incur a lot of latencies if a packet arrives and now it has to wait for the next CDRX cycle. Because of the drift, it just missed its current transmission times. So with enhanced CDRX and enhanced configured grant, a lot of techniques and options are being put in place, and they're still in discussion to how to align the CDRX cycles to the multimedia cadence. Release 18 also enables devices to sleep after uplink transmission. And an example of that is retransmissionless configured grant. As shown here, the idea is that if you have a legacy device, what happens is if you have a configured uplink configured grant, there is a pose information that gets transmitted, and then it may have to wait for an HARQ ACNAC and then decide to retransmit again. By doing that, the device A has to stay awake, it has to monitor control channels and so on, which wastes power. In release 18, what has happened is this: by using this technique called retransmissionless configured grant, you use a conservative MCS and there's no need to wait for retransmissions. And by doing that, you incur lower latencies, i.e. you incur lower power as well as lower latencies. Release 18 also, as I was saying before, takes a lot of emphasis of multimedia into account. For example, here's a picture that shows how the XR traffic flows from application server to the RAN scheduler. And in release 18, we have defined QoS based on multimedia frames or slices of a video frames, instead of prior releases which define QoS in the form of IP packets, for IP packets. By doing this, and by defining the concept of PDU sets, we enable really the RAN scheduler to ensure that a PDU set or a slice of a video frame can be scheduled in its entirety and ensure that they arrive at the receiver in time to be decoded, and also satisfy the multimedia constraints and the QoS constraints at the multimedia layer. Another example of this is application traffic staggering, wherein release 18 has put in features that enable the RAN feature, the application server to communicate to the RAN scheduler and really stagger these traffic arrivals. So as you can see in this picture, in the top figure, if the packets corresponding to the UEs are not staggered, they can arrive all over the place. And that makes for a really inefficient scheduler, meaning it has to now intersperse these packets as it's scheduling in the downlink, which may also cause higher latencies or also higher power, because now the device has to stay longer to receive all the IP packets corresponding to a slice of a frame or a frame. But if these UE traffic are now staggered from the server to the G node B, as shown in the bottom figure, then these packets can be staggered and they arrive in a chunk, makes life a whole lot easier for the scheduler. The device can also quickly go to sleep, because once the RAN scheduler schedules a slice of a video frame or an XR burst, the device can decode it and go to sleep. Release 18 also improves mobility management. In the case of release 15, a lot of the mobility signaling was using RRC signaling or L3 signaling, and that had incurred its own handoff delays. So there are proposals that Qualcomm is making in release 18 to use L1, L2 signaling for faster P-cell updates. And this has the effect of reducing handoff delays and extending coverage, which will become important as this technology, as XR gets deployed in a wide area network. And all these features are still in discussion. So please stay tuned and follow the progress over the next year as these features are more heavily baked into the standard and the specifications solidify. So this then, all our work so far, right, whether it is our on-device APIs, our 3GPP features in release 18, 15, 16, 17, all this really sets the platform for 6G. And 6G, one of the key underlying themes is really the merging of our worlds, the physical, digital, and the virtual worlds. And there are a lot of underlying technologies that are going to power it, such as AI native end-to-end communications, continued air interface innovations, as well as spectrum expansion beyond, millimeter wave and beyond to also include terahertz, and which we'll actually get to in the next few slides, as well as the scalable network architecture and communications resiliency. So as we move towards 6G by the end of the decade, we believe that the 6G XR requirements, if we believe in this immersive world and a transition from smartphone to a more immersive world, will really be fueled by the digital twins and spatial compute. Digital twins are going to digitize the complex physical world into the metaverse, and spatial compute will really enable immersive interaction with 3D digital content, as shown in this picture. And what this is going to lead to is a significant increase in per user data rates. It's now going to be 100 megahertz to up to even 10 gigabits per second per user, depending on whether it's indoor or outdoor or the exact use case in mind. And all this is going to lead to an explosion in the network capacity requirements, right? 100x increase in network capacity. And this would mean that we'll have to tap into all frequency bands and not just sub-6. I think it has to be millimeter wave, newer spectrums in 7 to 24 gigahertz, as well as the sub-terahertz frequencies for select environments. 6G protocol also has the ability or can take into consideration of how to natively support distributed compute. As I already mentioned before, an underlying fabric to enable XR is this distributed compute architecture where workloads are distributed between on-device, the edge cloud, as well as the cloud, right? So, but now I think if 6G, if we believe in this communication between the glass, a companion device, and the cloud, all happening over 6G across a plurality of the spectrum, depending on power and latency and availability consideration, we can really incorporate the end-to-end QoS and session handling and try to sort of negotiate workloads dynamically across these different entities to deliver a much more seamless experience. And there's the entire workloads can be sort of sliced and diced, whether it's 6DoF or SLAM or hand tracking, facial expression, eye tracking, 3D graphics rendering, and so on, and camera processing. And where do you distribute these workloads depending on power considerations and latency considerations? And can 6G sort of bake it in natively would be very important. 6G can also fuse perception and wireless to improve performance. And there we're happy to share that, like in Qualcomm, we've already demonstrated how perception inputs can improve millimeter wave beam accuracy. We've used our Snapdragon XR2 platform, which has millimeter wave capability and also a rich perception stack, and showed and demonstrated that if we take into account the 6DoF pose and the depth maps and fuse that with millimeter wave beamforming, it can lead to a superior performance. So the way it will work is that the 6DoF pose and depth maps can be used to really get a very accurate picture of what are the dominant blockers in the room or in the arena? What are the dominant reflectors? Where are the signals coming from? You can really form an RF digital twin. And once you do that, and then you fuse that with the modem information, the RF signals which are collected by the modem, what it really means is you can be pointing at the right beam at the right time, regardless of whether there is blockers or reflectors or user motion, roll, pitch, and yaw motion, and so on. And that leads to superior performance. And we're going to showcase some more of this in our upcoming Mobile World Congress using our Snapdragon XR2 platforms. So please stay tuned. And 6G can now enable this both on the device side and on the network side. Perception services, like at both sides of the network, to improve the overall user experience. Now let's take a look at how Qualcomm Technologies is enabling the XR industry. We have platforms, and I've been mentioning that throughout this webinar, right? We had the Snapdragon XR1, XR2 platform, and more recently, we announced the XR2 Plus platform, which was in the Oculus or the Meta Quest Pro and the Lenovo VRX devices. We also have continued to work on software and algorithms and provide that to the end user, or make that available, the stack to the end user via our Snapdragon Spaces. And these algorithms can include 6DoF, SLAM, object recognition and tracking, eye tracking, video pass-through. And then with each passing generation, they are hardened to lower and lower power to enable longer usage of time. And also we have reference designs, and we actively use this in our labs. We share it with our partners to do end-to-end designs and to do end-to-end bring up to make sure that we have the best optimized system for best user experience. And we have the Snapdragon Spaces SDK. You can go to spaces.qualcomm.com and you can really download an SDK, buy a Motorola phone and a Lenovo Glass, and start developing applications. As of today, Snapdragon platforms are powering most of the devices in the industry. More than 60 plus devices have been launched, and you can find out more on our website and our press releases. As I was mentioning, Qualcomm also has a Snapdragon Spaces developer platform, wherein we have empowered the developers to create an immersive experience for AR glasses. We're targeting an open platform and an open ecosystem, and it paves the way to a new frontier of spatial computing. Our Qualcomm Ventures team have also, and our business units have also launched up to 100 million of Snapdragon Metaverse Fund to really encourage our partners and developers and startups to create a more immersive experiences for XR. So with that, I would like to take a step back and sort of go through some of the key points that we discussed in this talk. One is we showed that how 5G enables boundless XR at scale and is ready for commercialization. We discussed how VR is already ready. The phone to glass is like ready for prime time. And then we also discussed how Qualcomm enable rich on-device APIs with 5G optimizations, and also which enables the applications to access these APIs and enable a richer user experience and more efficient deployments. We then spent quite some time discussing the 5G standards evolution path from release 15, 16, 17, all the way to release 18, the work item and all the features that Qualcomm is proposing, and how we have a very strong evolution path for enhanced XR experiences, and how it sets the stage for 6G, where the underlying theme is really the fusion of the digital, virtual, and physical worlds. At Qualcomm, we're making Boundless XR possible. We're strengthening the entire ecosystem with our 5G modem APIs, our optimizations, our distributed compute architectures, our XR platforms and SDKs and reference design. So with that, I'd like to thank you for being in this presentation, and also would like to open the floor up for questions and turn it over to the moderator.
Great. Thanks, Hemant, and thanks everybody for tuning in. So you show Wi-Fi as the connectivity for AR in 1 to 4 years, but what about Sidelink?
Yeah, so if you actually take a look at our phone to glass architecture, right, what's happening is Wi-Fi is here and now, right? So you have a Wi-Fi 6 moving on to Wi-Fi 7. So very natural connectivity fabric for phone to glass will be over Wi-Fi. But then the phone will still have 5G, and it will then talk to the cloud, and you do need a low latency 5G connection and a low latency high performance Wi-Fi connection between the phone to the glass. So that's what will happen in the next 1 to 4 years. So beyond that, we have to see what are the use cases for a 5G based side link, the pros and cons compared to a Wi-Fi link, and that still needs to be studied.
Great. And how do you see the XR device evolution and rollout?
Yeah, so that's a good question. There are really two categories of devices, right? So one category are the standalone XR devices, and examples of that would be HoloLens or the Meta Quest Pro or the Lenovo VRX, which was in the news recently. And that's the standalone sort of mixed reality category, right? And that's targeting enterprise, maybe even home use case, as well as industrial use cases, gaming use cases. And over the next many years, like maybe the 1 to 5 year window, as these types of devices scale and gain traction in the market, a progression to 5G is very natural because of scalability in a private network and to offer the reliability, right? When you have a large number of like these devices. On the other hand, you have the second category, right, which is really AR viewers. And that is for wide area networks. And a natural progression path is for these AR glasses to pair with your phone over Wi-Fi. And as the applications there gain traction, longer term, we'll begin to see 5G also being put on the glasses, because then you don't have to have this reliance on the phone, and you could also talk directly if there are issues with the Wi-Fi link to the cloud, right? So 5G plus Wi-Fi enabled AR glass, starting with RedCap release 17 and moving on to 18, would be great. And longer term, as the optics and display and the perception stack and the power consumption improve, we see the standalone track as well as the viewer track merge into the next compute platform, right? That's like 5 to 10 years.
Great, thank you. And what was the limiting factor to have only 6 users per FR2 GNB and XR demo? Was it the amount of data to be transmitted?
Yeah, so that's a good question. So we had basically, we used X55 5G modem, and there were two things. One thing is on the downlink, each user is getting 50 to 100 megabits per second. So there's a lot of downlink traffic. And also on the uplink, the slot structure that we used was DDD-SU, downlink, 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 and then an uplink. So there's a lot of uplink bottleneck as well, especially in millimeter wave. And so those will get resolved as the 5G progresses through the releases. And in fact, we have shown that 6 user can easily go to 12 users in a single 100 megahertz band. And then you throw in wider bandwidth, right? You can go to 200, 400 megahertz, then it starts to scale. And then you add more G node Bs. And especially the beauty with millimeter wave is that it's very contained. So you can really flood your indoor millimeter wave, or like a private network with many G node Bs, and you can really have unlimited capacity. So hope that answers your question.
Yeah, wonderful. For your Boundless AR testbed results, what were some of the 5G and Wi-Fi challenges to overcome?
Very good question. When we started out, we first built the system. We put the end-to-end system together. We worked with Ericsson, and we very quickly we discovered that tail latencies, end-to-end 5G and Wi-Fi round trip times, and especially at the 99th percentile, is going to be very key for a good user experience. So we put in a lot of on-device optimizations. We had to go modify the stack. The processing has to be quite different. How you handle XR and gaming traffic compared to how you handle, say a smartphone, like a regular smartphone traffic. So we worked, quite a bit on that, and then we have exposed that via APIs now to like end user application. And the other thing that's going to be very important is applications and wireless need to work hand in hand in a very tight-knit fashion via our APIs, right? I showed that example where applications, every 10, 20, 30 milliseconds or so need to know what is possible in the wireless link and adapt its data rate. Otherwise, there's going to be stuttering, missed frames, the tail latencies are going to blow up, and it does not make for a good user experience.
Wonderful. In your studies and demos, did you evaluate or use out-of-order delivery?
We take a very holistic look, right? In the sense, every application via our APIs, we get to know what are the application requirements, meaning by what time do you need to deliver all the packets corresponding or all the high priority packets to be delivered to the application, right? And then that we learn via APIs. Once we do that, we take a very holistic look and we go across all the layers, right? I think I had a slide that says from the PHY, MAC, the RLC layer and PDCP layers, and we take into account packet prioritization to make sure really that the critical packets are delivered to the application in time, right? So it's a very holistic thing. It's not like a feature.
Yeah. All right, thank you. And what is your view on which compute workloads should be distributed between the device and cloud for XR?
Yeah, great question. And this is an area of active research. Like a very short answer would be anything that is low power and low latency, and that can be hardened, right? Which is the approach Qualcomm is taking. A classic example are a lot of the perception algorithms, whether it's 6DoF processing, hand tracking, eye tracking, and so on. So some of the initial processing can be done locally by using co-processors on the device, and then the rest, and then the other extreme would be 3D graphics rendering, right? Or high performance graphics processing or 3D reconstruction. They can be offloaded to the cloud where you have high performance GPUs or a PC, right? So this would be a very high level classification, and then what's going to be important, and we're going to show that in the upcoming Mobile World Congress, is based on your 5G and Wi-Fi link qualities, can you slice and dice further? Can you move really some of the processing dynamically between the cloud and the phone or the glass and the phone based on your dynamic power and link considerations, right? So that would be, that's an active area of research for us.
Super. So does 5G access on C-band versus millimeter wave have significance in terms of E-to-E latencies?
No, I think both are going to be important, right? So for example, millimeter wave is great for like private networks, right? And we have, in fact, our private network trials that we did was on sub-6 as well, right? So we have demonstrated on both sides It's just that millimeter wave has this much higher capacity. So as these devices scale, um, you will get a lot more capacity, right, by using millimeter wave, and it allows you to scale more, right? Otherwise, our end-to-end optimizations are applicable for both sub-6 and also millimeter wave. And of course, millimeter wave, we've also put in a lot of special modes for beamforming, right, which I was showing earlier in slides.
Okay. And for perception enhanced wireless, it's a very interesting concept. How big of gains do you expect to see here?
Yeah, this is an active area. In fact, we have in our test bed 5G, 6G test bed, we're actively working on it. We plan to demonstrate the gains at the next Mobile World Congress. The way to think about this is if you just have modem, right, and it has to do the best it can in terms of relying on RF signals, and then we have stellar algorithms for handsets. But when you throw an XR device and this 99 percentile latencies and then blockage and motion, like a lot more aggressive motion, then by using the 6DoF information and the depth maps, which is coming from our perception stack, we can really build a device can build an RF digital twin and know exactly where the blockers are, where the reflectors are. Once you do that and you fuse that with the modem information, we can make sure that the modem is always picking the right beam at the right time. We're seeing 5 to 10 dB of gains by using our XR2 platform, which has X55 modem. And of course, with each passing generations, our modem capabilities are also improving. But this is an active area of research, and we're seeing promising gains.
And are XR devices focused more on millimeter wave than sub 7 gigahertz?
No, it'll be both, as I was saying, right? Like for example, for VR, mixed reality, indoor environment, especially in industrial, if you want a lot of capacity, millimeter wave is a very natural candidate. Although sub 6 we can make it to work as we have done in our trials. For AR, anyway, you'll have a 5G enabled phone, which will have both sub 6 and millimeter wave. You'll need all the capacity you can get. So just reliance on sub 6 is not going to be sufficient as these services scale. And you have the Wi-Fi connection between the glass and the phone. So that is a very natural partition for the next several years. And then eventually you will start having sub 6 gigahertz based modems on the glass itself, right? And it can start with RedCap from release 17 onwards. And then with each successive generation, you will see a lower power and then lower latencies and so on. So I think there is space for both. It's really, but I think millimeter wave is going to be critical, especially as the capacity requirements begin to increase.
Yeah. And which of the 5G features that are coming in future releases are you most excited about for improving XR power, latency, capacity?
Okay. Yeah, great question. Release A18, there's a dedicated work item, right? So, and there Qualcomm is bringing a lot of features. And the thing that I'm most excited about is we've taken an end-to-end view, really putting the whole system together, whether it's multimedia, working with our infra partner, working on the device with our APIs. We've taken a holistic look and we realized that 5G and multimedia needs to work together, right? So we put in features like enhanced CDRX, which aligns the multimedia traffic cadence to the 5G transmission time. So that's the feature I'm excited about. And also defining QoS in terms of basically multimedia frames or like video slices versus just IP packets. And again, a lot of emphasis on keeping the end user application, the end user experience in mind. And then like features like retransmission-less configured grant, which allows information such as post to be sent, without retransmission. So these are some release A18 features which I'm excited about. And I think I had a slide that showed all the features that we are proposing. And then we also have some mobility features, right? So, but a thing to keep in mind is we don't have to wait till release 18, right? I've showed you plenty of examples where with the current 5G and by using Wi-Fi, you can get the phone to glass starting to get deployed now. You can also enable VR over private networks starting with release 15. So, but release 18 will help you to scale more.
And are you going to test network slicing and functional splits to improve the experience of low latency of end-to-end cellular networks dynamically in real time?
Yeah, I think, see, first of all, we believe that the QoS, right, the ability for the device to learn application requirements and map that to the QoS and work with infra is going to be critical, whether it's flow prioritization or sort of, achieving the 5 QIs. Right. So, and then beyond that, we are actively looking into what sort of delta or additional benefits that slicing can actually bring. But QoS with on-device APIs are going to be very critical in the near term, right? To essentially get it going.
Great. And how is 6G going to be better suited for scaling XR than 5G?
I think in a short, one-line answer would be capacity, 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 right? Because if you have digital twins, we're moving into a more immersive world, and also spatial compute, right? I think as we move into the worlds of digital twin and spatial compute, your network capacity requirements and your per user data rate requirements are going to blow up. That means you can no longer just be satisfied with a sub-6. You have to go look for new spectrum. You have to better harness millimeter wave spectrum, move into sub-terahertz, 7 to 24 gigahertz spectrum, also tap into unlicensed, right? So spectrum is going to be key. And then, as I was saying, taking a more holistic look at fusing perception and wireless and distributed compute and building in protocols that can enable them, like much more natively versus as an afterthought, right? Like is going to be, much more important in 6G.
Thanks. So for release 18 proposal to align with the 8.33 millisecond cadence of XR traffic, this would seem to have a major impact since the entire 5G and our PHY is built around 1 millisecond boundaries. How would this work?
Yeah, I think Qualcomm has detailed proposals, so I would encourage you to sort of track that. And I think a lot of options are being discussed, right? But the end goal is to really get that alignment. There's a frequency approach. There are some formulas which are being defined. So it's hard for me to get into the nitty-gritty right now, but I would track the Qualcomm proposals in 3GPP release 18, and they're still getting defined. So over the next year, the spec should get firmed up.
Wonderful. I think we have time for one more question. So for the modem APIs on the device, how will the API be exposed to developers, OEMs, etc.?
Great question. From Qualcomm, we have the QE SDK or Qualcomm enhanced SDK. Right, wherein if you have an application on the phone, we can now enable these 5G modem APIs to the application via QE SDK, and they're starting to get rolled out. Yeah, that would be one pathway, right? So, and then you could connect with our product management teams on 5G to actually learn more and see how you could, avail of this.
Okay, great. Well, thank you so much again for your time. And I want to thank the audience as well for your great questions. And this concludes the webinar for the day.
Well, thanks a lot, Ben and the RCR team. And thank you for having me. And thank you all for listening to the webinar. It's been great. Thank you.
Great.